All right, in this video, we're going to review the idea of how we come up with the definite integral. So remember the process was that we took our interval from A to B, right? The interval, we're trying to find the area beneath the curve, and we subdivided, right? So we began by dividing it up into subintervals. From x0 up to xn, where we're using x or n different subintervals. Now, we typically did them all the same size. It actually ultimately doesn't matter as long as the size of the largest one goes to 0, as n will eventually go to infinity. And then the second step was we approximated the area of the subintervals, right? And the way we did it for the definite integral is we said, hey, the area for the ith rectangle, call it a sub I if you will, was just the function value at some point in the interval, which we called ci, times the width of the interval, delta xi, where again, delta xi was the width of the interval, and ci is in the ith interval. Okay, it's a point inside the interval. Okay. And then what we did is we said if we add them all up, then we'd have an approximation, right? Well, then we took the limit, and the notation that we used was this, limit as the magnitude of the partition goes to 0, and what that meant was the magnitude of the largest subinterval, because they didn't have to always be the same size. When we did them with Riemann sums, when we did them with left and right endpoint rules, we always did them the same size, because that was just the most convenient, but they didn't have to be. So we do the limit of that thing, and that type of thing is called a Riemann sum, right? The area of every one of those subintervals as I goes from 1 to n for our partition. And if that limit exists, then for that Riemann sum, then we say the function has an integral. And that is what we call the definite integral of our function. And so that was the definition of the definite integral. And those ideas that we used to originally develop the definite integral, those ideas now are going to become essential ideas, the things that we did, as we continue on, because we're going to be looking at other problems. Some of the problems we're going to be looking at are finding volumes of solids that are generated by doing something to the graph. Okay, and so we're going to be looking at some other things where we're going to need to derive and set up our approach here. Okay, and the idea is we need to follow this same process that we used for our definite integrals originally. And that process can be thought of as a 5-step process. First thing is to subdivide the stuff you're trying to find, compute, area, volume, whatever it is. Then we approximate one of those things, one subinterval. We come up with an approximation for it. We then add them all up. That's where the sum comes into play. We take the limit of that sum, which transforms it into an integral. So refer to this as the Sally approach. S-A-A-L-I, Sally. Subdivide, approximate, add, limit, integrate. The main ideas, though, really are going to be these two right here, the idea of subdividing and approximate, eventually taking the limit, which will transform it into an integral formula that we'll be able to use. So those are going to be really the main things, how we go from subdividing and approximating, because now it's really just doing a limit and a sum, which transforms to an integral, and how the stuff here, what it looks like as it's part of an integral. And we're going to see this over and over as we continue on. But of course, not only did we have that result that allowed us to do definite integrals, that eventually led to the fundamental theorem of calculus, which we can use. All right, fundamental theorem of calculus. And what that told us is we say let capital F of x be an antiderivative of little f of x. Then the integral from a to b of little f of x dx, remember, was to evaluate the antiderivative at the two endpoints and take the difference. Was to evaluate the integral at the two endpoints and then take the and then evaluate it, take the difference between those. All right, so that was our fundamental theorem of calculus. And that will allow us, once we have an integral, to be able to compute these things without having to think of it in terms of a sum or a limit. So let's do one example here, just to review, because we're going to do some more of this later. But for now, let's just do one example here. Let's consider the integral from 0 to 4 of the square root of x plus 12 dx. So we want to evaluate this definite integral. We happen to have a composite function here. So first things first, I'm going to do a little bit of transforming here. Rewrite that square root as x plus 12 to the 1/2 so that it's in terms of a power now. Right? And then we go with our normal substitution here. We go with our normal substitution here. Let u become x plus 12. du is going to call for just a dx. So we have everything I need to carry the integration through. Now those limits 0 to 4 were limits in terms of x. So I'm actually just going to leave it blank for the moment, because we could go back and compute u when x is 0 and compute u when x is 4 if we want. Or we can just always convert back to x later on. And in this particular example, I just want to wait and convert back to x later on. So we have u to the 1/2. And so simplifying here, integral of u to the 1/2 would be 2/3 u to the 3/2. Okay. Now we don't worry about the plus c because we're dealing with a definite integral. So now I just convert back over to x, and I'm going to evaluate it. It's x plus 12 to the 3/2, and now I switch back to my limits 0 to 4. And now we can work that integral out. So 2/3 of, and then what do we have here? Well, first we evaluated at 4. 4 plus 12 will be 16. And so that's going to be 16 to the 3/2 power. You can do that one of two ways. You can raise 16 to the 3rd, then do the square root, or do the square root and raise it to the 3rd. And in this case, I'm just going to go ahead and do the square root first. So 4 plus 12 would be 16. Square root of 16 is 4. 4 to the 3rd would be 64. and then we plug in 0. 0 plus 12 will be 12. So that's going to be 12 to the 3/2, or square root of 12 to the third. And at this point, I'm just going to go for the calculator approximation here. So just pulling up simple calculator here and just do the quick little calculator approximation. 64 minus square root of 12, all that raised to the third power. And so we get about 14.95 approximately. So we're going to be doing plenty more definite integrals later. I just wanted to bring one out also because we're dealing with the integration with the chain rule as well.